I'm Okubo from the University of Tokyo. I'm participating in my capacity as a member of SQAI. Please visit the booth if you have a chance. I specialize in tensor networks, so I would like to talk about the relationship between tensor network and quantum computing. Before I begin, in addition to this project, there's another quantum software endowed chair project. This is a little bit smaller, and I would like to introduce to you what we do there. This program started in 2021, and tensor network sampling is used for quantum machine learning and quantum application, and also we want to develop application inspired by that. Now, Dr. Todo and myself, as well as SQI related members, are included in the faculty. This is an endowed chair, which means that many companies are providing support, sponsorship. So, with the support of the University of Tokyo and the sponsors, we are running this endowed chair, mostly focusing on human resource development. Twice a year, we hold quantum software symposiums and workshops. We also hold lectures for postgraduates. We also have open seminars for general audiences, quantum mechanics and quantum mathematics. There's also hands-on program, and we also have seminars. We do the online seminar program 3 times a year. Next one is on the 9th of September. So if you're interested, please search on the web. We also have hands-on event. This deadline is has already arrived, and the hands-on program will be held the 29th of July. We also do some research in this program, but this endowed chair is such a small program with limited budget and staff. So we want to do research and education specialized in areas of expertise, specifically tensor network and the sampling, and I'm in charge of tensor network. We also want to promote research on quantum-inspired classical algorithms and classical-inspired quantum algorithms as well, not limited to quantum computing. And we want to utilize the advantage of having various sponsors and cooperating companies. So companies and university can work together for planning and operating the programs, providing a broader perspective in terms of education and research. If you agree with the purpose of this endowed chair, please let us know if you're interested in helping us. Now let's turn our attention to the main theme, tensor network. Tensor network and quantum computing are related to each other, but I would like to start about the tensor and tensor network and then how it relates to QC. This is the structure of my talk. Some of you are very familiar with tensor network, but others are not. So I will start with a very basic explanation, just to impress this upon you. Tensor is basically generalization of vectors and matrices. If you have seen this before, you would know that this is the diagram that represents a tensor or vector or matrix. And the leg that is growing from the tensor, this is called the bond dimension. And this dimension determines the accuracy as we try to describe different things with tensor. The most important calculation for tensor is contraction. So this is a matrix multiplied by matrix, and it then generalized into tensor. Visually, I think this diagram is probably the easiest to understand. If you connect these bond dimensions, then this is a contraction calculation. So when multiple objects are linked by the line, you can understand what kind of calculation is taking place. I'll not use too many formulas, but I would like to use diagrams to explain what is happening. Now, tensor network is based on contractions. Multiple small tensors are connected into a network. But there are so many different types of tensor networks. It can be used to describe so many different things. And I would like to talk about two basic classifications. So once the tensor network is established, do you have open legs? And if you have open legs, this is what it looks like at the bottom of the slide. In this case, the result itself is one big tensor, but if there are no open legs, if all the legs are connected to other dots, in this case, this is not tensor, this is actually representation of a number. And then the network structure could be regular, like right top, or it could be irregular, like right bottom. There are different patterns of network structures, and depending on the problem you want to solve, the network structure will change. Now, tensor network can relate to so many different themes. For example, for this meeting, I would like to talk about quantum circuit. Quantum circuit can be understood as a tensor network. And a while ago, quantum supremacy was achieved by Google, according to their contention. And then this is the circuit that was taken from their paper. So 1 qubit gate and 2 qubit gate. And then this is general qubit, and this is the quantum circuit as a whole. So points connected by the line is contracted. So this is the rule of the tensor network. And this is a quantum circuit, but you can also interpret it as a tensor network. Now, when you simulate quantum circuit, state vector simulation is from left to right, and this is according to the time extension. But if you can think about this as contraction of a tensor network, and you can calculate, formulate the simulation based on that understanding. And based on this idea, you can optimize the sequence of contraction, and we know that we can speed up the calculation. In 2021, Gordon Bell Prize, HPC, great prize was given to this research. So random circuit classical sampling was solved or simulated using tensor network. And Google's method would take 10,000 years, but through optimization using GPU, this was reduced to 304 seconds. And with quantum computing, it was 200 seconds. So even at the time, it was comparative. So classical computing can do really good with tensor method.
Other than that, there are many other examples of tensor network, but example related to quantum would be this. You might have seen this, but many quantum many-body state is where tensor network is used. And what's relevant is there are many qubits, quantum many-body state. So that's depicted by tensor network. Specifically qubit 01 against that other quantum overlay, overposition. If there are n qubits, then there are n legs. So n with tensor with n legs. So that way of description is the perfect, but it requires information of 2 raised to the power of n. But by using a tensor network, so entanglement, quantum entanglement, that's original, that's used. And by selecting the network that's representative of that, against the number of qubits, the linear extension is the necessary number rather than the exponential number. And related to that, in reality, if we are interested in the substance and if we want to know the low energy state of that substance, then rather than entanglement area low is known by using area low. The PEPs, by using that we can do the highly accurate approximation using a tensor network, which I am coming back to later. Other than that, I have been talking about quantum, but other than quantum, tensor network is used for other things. Due to time constraint, I cannot talk about details, but as I said, tensor network itself is very much related to quantum. So after describing quantum with tensor network, that can be converted into quantum. So if you're interested, you can come to SQA booth, where you can find various examples. What I want to talk about here is the use of tensor network to the data science. So quantum multibody state is what tensor network can be applied to, but other than that, many things can be described by tensor network. In this case, contrary to the low energy state, tensor network structure is not always favorable, but tensor network approximation is used in many cases. For example, the image data set. Let's say we have image data set and 32 multiplied by 32 pixel and 3 colors and 7200 data set. So it can be seen as a tensor with 4 legs. So that's divided into rings. Then for each tensor, data set information is concentrated, and that can be used for extracting features and tensor ring approach, and also neural network. Deep learning neural network can be divided into tensor network, and while attaining the accuracy, the necessary parameters can be reduced to achieve lightweight model. So tensor network can be used. And recently, other than that, partial differential equation can be resolved with a tensor network. This is the equation. This equation, by dividing it into grid, tensor network approach can be used to describe that, and the data can be contracted or compressed exponentially. So each point of grid information on the grid can be converted into quantum network, so it can be described with quantum computers. So the image is rough, so I cannot go into details, but compared to direct simulation, tensor network can produce the highly accurate calculation. That's what the paper explains. So like this, tensor network can be used for many things, and at the same time it can be embedded into quantum computers. So in that sense, quantum tensor network in the near-term future is very important in the application of quantum technology. And finally, tensor network and quantum calculation, what is the relation in between to conduct a survey? We've recently conducted an experiment. Rather than using tensor network directly, what we've done is tensor network was used on the classical side to compare against error tolerant, fault tolerant QC. And myself and professors from various universities worked together. And so FTQC was created, and so everyone believes that there's potential to efficiently solve many body problems in quantum physics and chemistry. One candidate is quantum phase estimation. So the approximate ground state is entered, then a time evolution is conducted, and eventually accurate energy value and ground state is obtained through the algorithm on the side of quantum computer. So calculation time is the polynomial time cost. From the side of classical computer, the technical calculation could involve the exponential cost, but by actually the potentially a polynomial can be used. So whether quantum computer has superiority over a classical computer, when such superiority is observed, it's not evident. So we have estimated the execution time by quantum computer and classical computer, and what are the occasions when the quantum computers show some superiority, and we have checked. And then here is the setup of the meeting, and quantum multibody issue was considered, and the energy difference is 0.01. And what is the execution time? Execution time required to determine the ground state energy with an accuracy of delta E. And the target is the typical many body system in condensed matter physics and two-dimensional J1, J2, and Heisenberg model and two-dimensional Fermi-Hubbard model. Against them, L multiplied by L square lattice, on top of which the simulation is conducted. And on the side of quantum computation, the execution time for quantum phase estimation is done. So a ground state is prepared, and the time is evolved, but there are many things, but based upon our estimation, dominant part is time evolution. So optimization of quantum circuit was also involved. On the side of classical computation, the tensor network method is considered as the most formidable. So MPS and two-dimensional network PEPs, they were used to do the estimation on the side of classical. And finally, the colors are gone, but here is the result. On the right-hand side, you see the result. On the left, J1, J2 Heisenberg model. On the right, you see the Fermi-Hubbard model. And the colors are gone, so it's difficult to see, but horizontally, you see system size, and vertically, you see running times. And these are symbols. The tensor network calculations and the red-blue lines are the qubitization. As the system size gets bigger, the quantum has a superiority. But in our problem, we came up with 100 quantum bits and several hours of execution time. There's intersection. That's our argument. So what do you see on the right? So what are the occasions where the quantum has superiority over the classical? So for example, the prime factorization used for cryptography, it takes a lot of qubits, takes a lot of time. So the quantum technology, many hours are needed, but the physical property technology execution time is only a couple of hours, and the necessary qubit is limited. So to realize quantum superiority, it's a good platform, and physical property problems seems to be the problems. And the tensor network can be applied to many problems. That's the message. So it's related to quantum circuit. So other cases can be converted. And finally, in the physical property problems, as I mentioned, tensor network and quantum can be combined to generate synergy. So these examples can be seen at our booth outside. Thank you. Thank you for listening.